We traditionally think of matter in four states: solids, liquids, gases, and plasma. It turns out that with quantum mechanics in the extreme cold, you can discover a whole new state of matter. On the quantum scale, it's impossible to know both the position and velocity of a particle at the same time. When we try to observe a particle's position, we must shine light, consisting of photons, onto the particle. Although this tells us the particle's position, when the photons from the light shined bumped into the particle, they changed the particle's course, preventing us from knowing the velocity. So we can only represent particles with wave functions, where each point on the wave represents the probability of the particle being at a certain position at a certain time. However, this is only thought to be relevant when talking about extremely small things. What if we could observe this on the macroscopic scale? If we have a gas of bosons, an extremely low temperature approaching absolute zero, and an extremely low density, it turns out that we create a whole new state of matter called the Bose-Einstein condensate, where particles lose their individuality and start acting like a superatom. This is because all particles have their own quantum states. A quantum state consists of all the variables describing the knowledge we have of some particle. Under extreme conditions, these particles begin to occupy the same quantum state, meaning one wave function represents the entire system of particles instead of just a single particle, hence the name superatom. At this point, we've left the conditions of temperature and pressure in the ordered state of matter, where solids, liquids, and gases exist, and entered the quantum critical state. But why is this important? Well, the Bose-Einstein condensate gives rise to superfluidity, which is when a fluid flows with zero loss of kinetic energy. The fluid will rotate indefinitely when stirred. In the case of superfluid helium-4, its high thermal conductivity makes it great for cooling high-field magnets, which are used in MRI machines, power generation, nuclear physics, and much more. The first creation of a superatom in 1995 revolutionized the way we understand quantum phenomena, making way for the exploration of many more fundamental questions in physics.